Hello everyone, thank you for the introduction. Yes, so Fazle, Professor Fazle Hussein was not able to be here because he had a medical situation. Is better? So he went to doctors, the doctor suggested advised not to travel, so he requested me to give the talk today. So I will be talking about pretty much mostly his work, but also part of what I've done is in collaboration with Professor Ye Yao, who is actually in Beijing Institute of Technology. He was his former postdoc, and we'll talk about various vortex dynamics in various vortex flow phenomena. Okay. So I will start with some examples, and here we see this is a wake of an airplane, and as we all know, wake is dominated by two counter-rotating vortices, and you see these are very large vortices behind, and these can be a hazard of an airplane flying behind because they can induce some roll and even affect the flying of vortex behind, of airplanes behind. So these large vortices actually are a problem, particularly for having many flight takeoffs, one behind the other. So you'll see if you go to the airport, there is a long line and wait time. So if we are able to solve this problem of this air traffic capacity, which is a crisis, and as an example, here is every dot here is an airplane flying simultaneously in America. So if we can improve this wait time, it will save a lot of fuel and money in many aspects of the economy. So this is an important problem which involves vortices. Another example is in the defense and national security. This is a fighter jet. You see these are visualization of vortices on the airplane, which affects the aerodynamic performance. In the case of submarines, we want to have very quiet, and if you understand the vortex dynamics, you can address the problem of noise generation, even drag. In case of torpedoes, noise generation in helicopters. So these flows are very relevant, and vortex dynamics is very important to understand. Right? Also, the wind energy industry. You see the wake of horizontal axis wind turbines is dominated by three helical vortices, and this wake interact with downstream turbines. So if we want to, let's say, optimize the power generation of a wind farm, we need to understand the vortex dynamics to improve the power generation of a wind farm. Okay. Similarly, these are very prevalent in nature. See, it was already mentioned. Hurricane is a vortex. Tornadoes, even astrophysical jets, you can model by vortex. To understand why bird flies in a V formation, they essentially take advantage of these vortices left behind of the first birth, and also why birds are one behind the other, taking advantage of the wake. In this case, it's not so much a vertical flow, but it's to understand the difference between the two is a vortex dynamics problem. So these are examples, like you see trailing vortices, wind turbine tip vortices, and these are actually very prevalent in turbulent flows. And turbulence is prevalent in nature, technological, and control of transport phenomena, in transport phenomena problems, right? There are three approaches that most people follow, and this is the statistical, or others do structural, dynamical. But in our group, Fazle has tried to address all the three together, right? And one main claim he has been saying for maybe 40 years now, that although the turbulent flows are apparently random, he's been claiming for a long time that there is order within disorder. And he popularly called this order as the coherent structures of the flow. Or more specifically, the vertical structures of the flow, the vortices that are in the flow. This is the order within disorder. So you see these coherent structure, vertical structure are characteristic, and for many turbulent shear flows, and these are very important to control these flows. As an example here, I'm showing an elliptical jet that if you follow the evolution of this elliptical jet, ring, which is coming from an elliptical jet, this ring, you see the axis will flip. First it's vertically, but after some time it becomes horizontal, which will affect all the underlying turbulent flow. So if you understand this dynamics of this coherent structure, we are able to control. And he also has been claiming for some time that if there is no coherent structure, no vertical structure in the flow, you cannot control. So coherent structures are the muscle and voice of turbulent flows. In the early times, they actually visualize coherent structures and vertical structure by smoke and dye, which is a scalar field, right? But this scalar field, it can be very misleading, even when the Schmidt number, so the diffusivities between momentum and the scalar field are equal to each other, Schmidt number equal 1. Even in that situation, which is not common in real flows, you will see when you compare with the, let's say, vorticity equation, there is a very important term missing, which is the tilting and stretching term. And this one is important because if you have in any given flow strong stretching, what it will do is essentially deplete the scalar field. So any visualization via scalar field will be very misleading, and this actually was verified in his early work when he did some simulation. Here is a simulation of two vortex rings colliding at an angle. On the left, this is the vorticity magnitude, and on the right is the scalar field. You see at the beginning they're similar to each other, but after a while they're quite different, and the main differences are in the regions where there is strong stretching. So he showed that this is misleading way to do visualizations. Okay? So he wanted to give some quantitative way to actually uncover these vertical structures in random flows, turbulent flows. So how to study this coherent structure, vertical structure, how to extract the structure, the organized part of the flow. So we will try to, he actually proposed this decomposition of the flow, that in any shear flow, you can decompose in a coherent vortex plus a fine scale turbulence. So once you identify the coherent part, the remainder is just the incoherent turbulence of the flow. And this is a methodology that he started, let's say, how to reduce the coherent part of the flow, the vertical structure. If you start with any given flow, let's say mixing layer, jets, homogeneous shear flow, wakes, channels, boundary layer, and then you do some measurements, and this is the field you will obtain even from simulation, by the way. It doesn't need to be an experiment. Even in simulation, if I measure velocity, this is what you get, which is apparently random. But then if you go another step and then you smooth out and compute vorticity, which I will address more details about vorticity later. But then when you look at the vorticity field and then you smooth out, you will see that there are many vertical structures of different sizes, orientations, and strength, right? But then you will see that there's some structures that are prevalent and repeat in the flow in many parts, and these are more strong affecting the general flow. So once we identify these points and consider these flow features as important in the particular flow, then you have to go back. You see these plus signs identify the exact location of these structures that we now care about, and then we perform a phase log ensemble average, right? And by doing this process, you essentially, this process is a little bit iterative because not one structure, even with similar features, will be exactly aligned with each other. So you need to go through alignment process and cross-correlation between structures. And then after that process, which is actually an iterative process, you end up obtaining, or what he called educing, the coherent structure, the vertical structure of the flow. In this case, this is for a mixing layer. This is a classical result, which is very interesting, I want to emphasize. You see in the left, this is the coherent vorticity field, which essentially is capturing the vertical structure present in this flow by phase log ensemble average. And you see, we are actually capturing the rotating part of the flow, but also these other regions which he called the saddle points or the braids between successive span-wise structure, because in a mixing layer, the dominant structure is a span-wise vortex. But once you do go through this process, you can also take a look at other additional coherent measures. And here on the right, I'm showing details of these coherent measures. And for example, while we have the rotation and we are able to find the center of this structure, when we look at the coherent production and strain rate, it's not actually in the rotating part. The peak of turbulence production or coherent turbulence production happens to occur at these braids, which is where there is no much rotation, right? And also the turbulent Reynolds shear stress is also maximum at the braids, which is on the sides of this rotational part. And this rotational, what it does is actually collect that turbulence and put it together at the center of the vortex. So this is very interesting. I wanted to emphasize, work in the 80s. So that was earlier, that was how to do the way to reduce the structure a quantitative way, but he also wanted to understand vertical structure from more analytical way, and that's where he came to his work on how to identify the vortex. We've been talking about this last 2 days. There were some proposed strategies also mentioned, like Q criterion, delta, and even some by regions of low pressure. So he proposed this, in that time, is a new vortex identification method, also widely mentioned these days, is the lambda 2 criterion. And he showed that by looking at this tensor you see here is a square of the strain rate tensor plus the square of the rotation tensor. When you do the decomposition of symmetry and antisymmetry, the regions of negative lambda 2 are the vortex core, he claimed. He even showed that you need to be careful with even other identification criteria, because they don't quite give the same flow, particularly when the flow is three-dimensional, like in this case we're studying a swirling jet impinging a wall. In two dimensionals, they're very similar to each other, right? And I have to say, more recently, we are also evaluating, actually learning and evaluating the Lutex, and see how can we use this new method to see if we find new insights on these flows that I will be mentioning today. And here's a summary of all the aspects of coherent structure dynamics that Fazle has addressed through the years, so it's very extensive, so I will not go into those details. So I will start with some aspects more specifically he addressed, and here I already gave the motivation. We care about this vertical structure, the coherent part of flows, but often they show up as embedded in fine-scale turbulence, like in any shear flow. Well, first thing he identified that when we put this coherent structure in fine-scale turbulence, this large-scale vertical structure undergo variation of their core, and this he called this core dynamics, which are very particular. We'll go in more detail. But here is just one example of where he studied the vortex column embedded in fine-scale turbulence, and you see what is the process of how the small-scale turbulence evolve by the effect of the coherent structure, essentially organizing the fine-scale turbulence into a series of dipoles that are vectored outward, radially outward from the center of the vortex. Also, you see that the core is not exactly uniform. There is some variation of the core diameter of the large-scale structure. Here is more details. So you see this. Initially, you have this series of dipoles that eventually they die out because of cross diffusion. But then some of monopoles, they actually survive, which are those that affect back the large-scale vertical structure, inducing some core dynamics. This is interesting. This is an additional study on how this is important particularly as you increase Reynolds number, these dynamics become much more complex. And there's many details on this work, which again, I will not go. I will just mention some key results. This is a more recent study where he's using a vortex column, also with a ring embedded in fine-scale turbulence. And you see, not only there is organization of these small-scale turbulence, there is a hierarchy of alignment of some of the vertical structures. You see, you have a big vortex rod, then the ring, big organized, smaller structure perpendicular, with axis perpendicular to the axis of the ring, while the ring is also, axis is perpendicular to the vortex column. And here's more details of this simulation. So now we'll kind of change topic, and here is one problem he has been addressing quite a bit, is the vortex reconnection. So vortex reconnection is if you consider two antiparallel vortices, both perturbed, they will, by mutual induction, they approach each other. And then they will collide, and then when they collide, there will be a change in the topology, right? Because you see here is all blue on the left, red, but when they collide, they undergo a process of reconnection. And then you see part of the blue is connected with the red and red with the blue, and then they move away from each other. That is a change in the topology, right? And this is important problem because even if you go back to the wake of the airplane, you see this process of vortex reconnection again is prevalent in many technological applications, like in the wake of airplanes. You see, you have two counter-rotating vortices, they being perturbed by atmosphere, and then they reconnect and forms a series of rings. So again, also understanding this, it will be important to how airplanes need to behave behind another of each other. What are the important characteristics of vortex reconnection? So in viscous vortex reconnection, he said that the reconnection is never complete, to contrast with what people also have studied, which is the quantum vortex reconnection, which is a complete reconnection. What I mean by this is, in viscous reconnection, this is a now more localized of the process of reconnection, that when after the process of reconnection, you can see here is a formation of a bridge, which is this part. But then there is some vorticity left behind, and these are the threads. So this is what it means by incomplete vortex reconnection. It's just there is some circulation left behind, and this is never complete in a viscous, which are the more common process of vortex reconnection. So here is actually a plot showing the transfer of circulation transfer between the first vortices to the bridge. You see, it never goes to zero, so there is actually 30% of vorticity left behind in these threads. And I will go in details of why these threads are important, particularly for understanding turbulence cascade, for example. Okay, so he, with Jie Zhao, he recently did interesting studies of vortex reconnection at high Reynolds numbers. And one important thing is he find that this, previously he taught us very simple threads, but as you increase Reynolds number, these threads become very complex with many different vertical structures in between. You can even find some vortex rings, secondary bridges, and so on. So it's not as simple as we thought initially. And even if we continue to increase Reynolds number, he found there is, in reality, it can be a cascade of vertical structure from big to very small scales, and this is what kind of promoted the discussion of vortex reconnection as a model for physical model for turbulence cascade. And here again is some more additional details. So before we didn't know there is fine scale turbulence also at the bridges, not only at the threads, which is very complicated, and hierarchy of vertical structures organization and so on, but even at the bridges is very interesting. Also, we have studied vortex reconnection embedded in fine-scale turbulence. Again, there is quite asymmetric process and very complex. So now I will go into details of why vortex reconnection is important. So maybe I think 40 years ago, he proposed or suggested that vortex reconnection is the source of noise generation. Although at that time he was not able to fully show or prove this claim. But the process is that, for example, noise generation in a jet, essentially you have a jet, you are forming series of vortex rings, but these vortex rings get perturbed, and when they have these wiggles, they end up reconnecting into a series of smaller rings. They end up affecting. So he showed that indeed this is how more recently they were able to prove that this is indeed the case. So I guess I will try to go a little bit. Yeah, so here is this is the method of physical method for vortex reconnection. So he said it's a successive process of reconnection into smaller and smaller structures that the threads undergo additional reconnection and so on. And this was actually verified in this work, because you can see evidence of that initially proposed simulation. So I will go a little bit faster. He also wanted to addressing the problem of singularity of the Navier-Stokes equation. He showed that the important aspect left behind is that in the collision of the vortices, reality the core of these are not circular, incorrectly assumed by Moffat and Kimura, and then that's why there is not continuously increase of vorticity. He had many other works. I will just, for the sake of time, will go a little bit faster. He did a lot of work in helicity. For example, there was a claim that helicity remains conserved after process of vortex reconnection. He showed that this is not the case. Actually, there is quite an increase of helicity. These are the details of core dynamics, which I will skip now. Another aspect of flow here studies, core dynamics can erupt. This is vortex bursting due to strong core dynamics. You can have a generation of additional vortices that move radially outward, and this is here clarify what is this so-called bursting. And of course, this is the study of transient growth in turbulent boundary layers, where he showed that transient growth, even though all perturbations are decaying, he showed that a perturbation can actually increase through this strict transient growth mechanism, even generations of stringwise vortices that are essential of near-world turbulence. Okay, and then he did some other studies based on that initial work of transient growth, addressing the problem of drag control. So I think I will stop here. It's basically a summary of many works that he has been addressing through the years, and if there is any question, I will gladly address it. Thank you.